Hi everyone, so this is the second video on the topic of dimensionless groups. In the first video, we went through a problem that has implications in real life research, and we were asked to find dimensionless numbers based on five physical quantities: diameter, viscosity, density, stress, and gamma, which is the surface tension. And we used Buckingham-Pi theorem to evaluate that there are two independent dimensionless numbers, and then we also used Rayleigh analysis to exactly find what these dimensionless numbers are. So if you haven't had the chance to go through the first video, I highly recommend that you do that, because this video is actually sort of following up on the first video. So in this video, what we will do is we will try to find a dimensionless number without using the Rayleigh analysis, and I will try to show you that we can do that, and it's actually very quick and not very difficult to do once you have some practice of it. So let me first again state the problem for you, that we had a droplet of diameter d, viscosity mu d, density rho d, and was being deformed by an external stress tau, and there's a surface tension between the two phases, and that surface tension is gamma. And again, Buckingham-Pi theorem tells us that there are five physical quantities and three dimensions: mass, length, time, MLT. So there will be two independent dimensionless numbers. In the previous video, we found three dimensionless numbers, n1, n2, n3, and showed that only two of them are independent, and that n3, we actually showed that n3 is a function of n1 and n2. So we basically can pick any of these two to be said as the two dimensionless numbers that are important to the system. So how do we do this problem without using any Rayleigh analysis? So a good point to start is actually go on table 1.6 in the textbook, which is on page 15, and sort of see the different dimensionless groups that have been given to you. So it talks about groups which are like ratios of different forces. So there are inertial forces, viscous forces, surface tension forces, and gravitational forces. What we can quickly see is that there is no gravitational forces, so that will leave us with only three dimensionless numbers from the table. That is Reynolds number, which has been defined in the table as rho u L by mu, Weber number, which has been defined as rho u square L by gamma, capillary number, which is the ratio of viscous stress to surface tension stress, which is mu u by gamma. And now we have to find two dimensionless numbers, but we had three. So it's not very difficult to see actually that Reynolds number is nothing but Weber number by capillary number, and hence actually we can pick two of any of these three numbers and call them our dimensionless numbers that will be relevant to the system. So let us say I'm picking Reynolds number and Weber number, and again we can pick Weber and capillary, or we can pick Reynolds number and capillary, but just for simplicity I'm choosing Reynolds number and Weber number. Now for Reynolds number and Weber number, we need to know what we will substitute for rho, what we will substitute for length, what we will substitute for mu, what we will substitute for gamma, and what we will substitute for velocity, right? For rho we can just use rho d, which is given in the problem. For length we can substitute diameter, because that's the only relevant length scale. For viscosity we can substitute mu d. For gamma we can substitute gamma. These are all like straightforward. You just have been given all these five variables here, and you just have to substitute exactly without any modifications. For velocity, this has not been given to us, and how can we substitute that? So velocity, I mean, this comes with generally sometimes practice, but you can imagine that rho d u square will have the same units as tau. And why am I writing tau here? Because this is a variable that has not been used till now, so I have to use it for velocity. So what I'm saying is that the tau has the same units as rho d u square. Both of them have the units of stress. You will sort of start getting this with more practice, but like this is something that you have to sort of guess, and then that way you can write like u as square root of tau by rho d. So rho d u square is actually inertial stress, and I'm just equating that to tau and calling u as a u as square root of tau by rho d. So this is something that will come with practice. I know this may sound that I just put it out there without any prior knowledge, but this comes with practice. You will see in problems when you do that, you start of realizing that we can basically sort of create velocities like this. Basically, the important thing is to be dimensionally correct. You can check that tau by rho d square root has the dimensions of velocity. So now I have everything I need for both Reynolds number and Weber number. So let's just start to substitute. So Reynolds number is actually rho u L by mu. So rho is nothing but rho d. U is nothing but tau by rho d. L is diameter, and then mu d, right? And if you rearrange this, this becomes tau into rho d square root into d by mu d. And if you write Weber number, that is rho u square. U square is square root of tau by rho d whole square, which is nothing but tau by rho d, right? Into length, which is d by gamma, and this basically rho d gets cancelled. This is nothing but tau d by gamma. And if you look at our solutions which we found from n1 and n3, they are exactly the same as Reynolds number and Weber number. So we didn't really have to do the entire Rayleigh analysis. We could have just come to this point by realizing that these three numbers, Reynolds number, Weber number, Capri number, are the relevant numbers from table 1.6 because there is no gravitational force. There has to be inertial force because there is density. There has to be viscous force because there is viscosity, and there has to be surface tension force because there is surface tension. So we just use these three numbers, and then we found the right length scales, density scales, viscosity scales, surface tension scales, and velocity scales. The only tricky part was what we should do for this velocity, and that's, I said, will come with practice. But basically, we used the only variable we didn't use tau, and said that tau will have same units as rho d u square, so that's scale velocity as tau by rho d square root, and then we substituted and we got the same results. So this is just sort of illustrating to you that there is another way other than Rayleigh method that you can do, and it's intuitive once you sort of start practicing it. So I hope this video was useful. Again, please go through the first video as well as this video to see two approaches of finding dimensionless numbers. And we'll be happy to take any feedback that you may have. Thank you.